On July 28, 1976, the Soviet Union fired more money at a single American aircraft than most countries spend on their entire air force in a year. 26 surface-to-air missiles, millions of rubles. The absolute pride of Soviet air defense screaming skyward. Rocket motors burning white-hot as they climbed desperately toward a black silhouette cruising at the edge of space over the Baltic Sea. Major James Sullivan, at the controls of his SR-71 Blackbird, watched his warning systems explode with alerts. 6 missiles, then 12, then 20. His cockpit blazed with threat indicators as more than 24 missiles clawed upward through the thin air, each one representing the concentrated fury of 3 nations' air defense networks scrambling to respond to his presence. Within seconds, air defense batteries across East Germany, Poland, and the Soviet Union had detected the intruder. SR-72 and SA-5 missiles roared from their launchers, their guidance systems locked onto the black shape barely visible against the darkness of near space. Each missile represented millions of rubles in Soviet engineering, the best air defense technology the Eastern Bloc could produce. Sullivan didn't flinch. He didn't evade, didn't even increase throttle. He simply watched as every single missile exhausted itself thousands of feet below his aircraft, tumbling back to Earth in defeat, their rocket motors spent, their guidance system still tracking a target they could never reach. This wasn't an isolated incident. This was Tuesday. Over its operational career, the SR-71 Blackbird would be targeted by more than 4,000 surface-to-air missiles. Not one ever came close to hitting it. The aircraft was, by every conceivable measure, Invincible, a titanium arrow that mocked the entire Soviet air defense establishment every time it took to the sky. And yet, the SR-71 is dead. Grounded, sitting in museums across America, while the U-2 is slower. More vulnerable aircraft, it was specifically designed to replace Still Fly's combat reconnaissance missions today. More than 60 years after entering service, 4,000 missiles couldn't kill the Blackbird. Something else did. What finally destroyed the unkillable aircraft wasn't Soviet engineering or advanced missile technology. It wasn't a breakthrough in radar systems or interceptor performance. It came from something far more mundane, far more predictable, and ultimately far more lethal than any weapon system Moscow could deploy. The SR-71 had a fatal weakness, and no amount of speed or altitude could overcome it. Before we dive deeper into this story of Cold War supremacy and ultimate vulnerability, if you're fascinated by military aviation history and the strategic decisions that shaped our modern world, hit that subscribe button. What you're about to learn will fundamentally change how you think about military power itself. Let's continue. The story of the Senior 71's weakness begins with understanding exactly what made it so impossibly dominant in the first place. To grasp why this aircraft seemed invincible, you have to understand the desperate circumstances that created it. May 1st, 1960, a date that changed everything. Soviet SA-2 missiles brought down Francis Gary Powers and his U-2 spy plane over Sverdlovsk, deep inside Soviet territory. The pilot was captured alive and paraded before television cameras. The aircraft wreckage was displayed to the world press. American reconnaissance capabilities and American credibility became an international humiliation overnight. President Eisenhower was caught in a public lie. He had initially claimed the aircraft was a weather research plane that had strayed off course. Soviets produced Powers himself, very much alive, along with the sophisticated camera equipment that proved the aircraft's true purpose. The diplomatic fallout was severe, contributing to the collapse of a planned Paris summit between the superpowers. The U-2 had been America's primary eye in the sky, photographing Soviet military installations from 70,000 feet with apparent impunity for 4 years. But it was subsonic, cruising at roughly 430 miles per hour. It was high, but not high enough. It could be tracked, it could be intercepted, and now everyone knew it could be destroyed. CIA Director Allen Dulles needed a solution immediately. He turned to the only man who might provide one, Clarence Kelly Johnson, the legendary engineer who ran Lockheed's secretive Skunk Works division in Burbank, California. Johnson had already designed the U-2. Now Dulles asked him to design something that would make the U-2 obsolete, an aircraft that Soviet defenses couldn't touch no matter how hard they tried. No matter how much they spent, no matter how many years they devoted to the problem. Johnson's response was characteristically audacious. Build an aircraft so fast and so high that Soviet defenses couldn't touch it because the physics of interception simply wouldn't allow it. Not just faster than missiles, faster than the physics that governed missile intercepts themselves. The SR-71 would cruise at Mach 3.2, more than 3 times the speed of sound. Over 2,100 miles per hour at altitudes above 85,000 feet. At these speeds, the aircraft would outrun its own radar signature. By the time Soviet tracking systems detected the aircraft, computed a firing solution, and launched their missiles, the Blackbird would be miles away from where they calculated it would be. The missile would arrive at empty sky while its target accelerated into the distance. What Kelly Johnson proposed wasn't just difficult. Most aeronautical engineers believed it was flatly impossible. The temperatures involved would melt conventional aircraft. The speeds would tear apart existing airframe designs. The altitude would put the aircraft in a region where air was so thin that conventional aerodynamics barely applied. They were almost right. What Johnson and his team accomplished remains one of the greatest engineering achievements in human history. The challenges facing the Skunk Works team were staggering in their complexity, and I find it remarkable that they solved them using 1960s technologist-slide rules, wind tunnels, and raw engineering intuition rather than the computer simulations and computational fluid dynamics tools that modern aircraft designers take for granted. The fundamental problem was heat. At Mach 3, air friction would heat the aircraft's skin to over 500 degrees Fahrenheit across most surfaces. Leading edges, engine nestles, and other high-stress areas would approach 1,000 degrees hot enough to glow visibly in darkness. No conventional aircraft aluminum could survive these temperatures. Standard aluminum alloys begin losing structural strength at 250 degrees and would literally soften and deform under Mach 3 conditions. Johnson's solution was titanium, specifically a beta titanium alloy called B120VCA that could withstand sustained thermal cycling without losing structural integrity. Titanium offered the strength-to-weight ratio needed for the mission and could maintain its properties at temperatures that would destroy any other practical aircraft material. But titanium presented its own engineering nightmares that nearly killed the program multiple times. The metal was extraordinarily difficult to machine. It work hardened unpredictably, meaning that the act of cutting it made it harder and more resistant to further cutting. It reacted violently with contaminants at elevated temperatures. Standard cutting tools would dull within minutes of beginning work. Specialized carbide tools had to be developed specifically for the program. Even tap water was dangerous. Chlorine in municipal water would corrode titanium at machining temperatures, compromising structural integrity. Skunk Works had to use only distilled water in all manufacturing processes, thousands of gallons of it. Cadmium-plated tools, standard in the aerospace industry, left deposits that weakened the titanium. All tools had to be specially sourced and certified free of contamination. A single mistake, one wrong wrench used by one tired technician, could compromise an entire structural component that took months to fabricate. The welding procedures were equally demanding. Titanium absorbs hydrogen at high temperatures, making it brittle. Every weld had to be performed in an inert atmosphere, with elaborate purging procedures to eliminate any trace of moisture or contamination. Welders worked in essentially laboratory conditions, following procedures that had been developed through painful trial and error. The procurement situation bordered on absurd dark comedy. The United States didn't produce enough titanium domestically for a project of this scale. The primary global source of titanium ore was the Soviet Union, through elaborate front companies, fictitious mining operations, and third-party intermediaries. The CIA secretly purchased Soviet titanium to build the aircraft that would spy on Soviet territory. The Kremlin was literally selling America the raw materials for its own surveillance. The irony was apparently lost on Soviet trade officials, who were happy to earn hard currency from what appeared to be legitimate commercial purchases. Here's where the engineering became almost poetic in its elegant pragmatism. The thermal expansion problem seemed fundamentally unsolvable. At cruise temperature, the entire airframe would expand by nearly a foot in length. Fuselage panels that fit precisely on the ground would have significant gaps at operational temperature or vice versa. No sealant existed that could remain flexible across a 600-degree temperature range, while also sealing fuel tanks against the volatile JP7 fuel. Every material that was flexible at room temperature would char and fail at cruise temperatures. Every material that survived cruise temperatures was rigid and brittle when cold. Kelly Johnson's solution was elegant in its apparent crudeness. Design the fuel tanks to leak on the ground. The panels were fitted with deliberate gaps that would only seal when the aircraft heated to operational temperature. Pilots would take off with fuel streaming from dozens of panel joints. Climb to altitude, light the afterburners to heat the airframe to operating temperature, and watch the leak stop as the titanium expanded and the gaps closed shut. Ground crews grew accustomed to mopping JP-7 off the tarmac before every launch. The aircraft that would prove invincible in the sky couldn't even hold its fuel while parked. This apparent flaw was actually a sophisticated solution to an intractable engineering problem. The panels were designed to fit perfectly at 500 degrees, not at room temperature. The Pratt & Whitney J58 engine was an engineering impossibility, made real arguably the most remarkable power plant ever created for atmospheric flight. At low speeds, it functioned as a conventional afterburning turbojet. Air entered through the inlet, was compressed by the compressor stages, mixed with fuel and ignited in the combustion chamber, expanded through the turbine to drive the compressor, and was further accelerated by the afterburner before exiting through the nozzle. Powerful, certainly, but conceptually similar to other military jet engines of the era. But push past Mach 2, and something unprecedented happened. The engine essentially transformed itself into a ramjet, a fundamentally different type of propulsion system. A movable, conical spike at each engine inlet would translate forward and backward with millimeter precision, positioning shockwaves to compress incoming supersonic air before it reached the compressor face. These shockwaves, invisible but immensely powerful, would slow the air from supersonic to subsonic speeds while dramatically increasing its pressure and temperature. At Mach 3.2, approximately 80% of the engine's total thrust came from the inlet system alone. The compression was so efficient that it generated massive thrust before the air even reached the combustion chamber. The turbojet core became almost secondary, essentially an afterburner for the inlet system rather than the other way around. This hybrid turbo-ramjet concept had been theorized, but never successfully implemented at these performance levels. The J58 made it work through engineering precision that bordered on the obsessive. Pilots called it the Beast. The name was earned through hard experience. If the inlet spike position was fractionally wrong even by millimeters, the shock wave would be swallowed by the engine, causing a violent phenomenon called an inlet unstart. The supersonic airflow would suddenly reverse direction, essentially backfiring through the inlet with explosive force. The asymmetric thrust from one engine unstarting, while the other continued producing power, would slam the aircraft sideways with brutal force. Pilots described the sensation as being hit by a freight train while traveling at 3 times the speed of sound. The aircraft would yaw violently, and crews had milliseconds to react or risk structural damage to the airframe. The inlet control system made constant adjustments throughout flight, monitoring airspeed, altitude, angle of attack, and throttle position to keep the shockwaves precisely positioned. The analog computers that managed this process were sophisticated for their era, but operated at the absolute edge of their capabilities. Colonel Rich Graham, who flew 187 missions in the Blackbird over his career, later recalled, "The aircraft was always trying to kill you. Every system operated at the absolute edge of what physics allowed." The SR-71 negotiated with it constantly for 3 hours straight. The moment you relaxed, the moment you stopped paying attention, something would go wrong. The engine's operating environment was brutal beyond anything experienced by other aircraft power plants. Inlet temperatures at Mach 3 cruise reached nearly 800 degrees Fahrenheit, hot enough to glow visibly. Turbine inlet temperatures exceeded 2,000 degrees. The engine produced maximum thrust continuously for hours. Unlike fighter engines that typically operate at full power only in short bursts during combat, the sustained high-temperature operation meant that component life was severely limited. The engines required complete overhaul after relatively few flight hours, essentially being rebuilt from scratch at enormous expense. Turbine blades would crack, seals would degrade, and thermal cycling would fatigue critical components. The cost of maintaining these engines would eventually become one of the factors that killed the program. The fuel was equally exotic and equally essential to the aircraft's remarkable capabilities. JP-27 was developed specifically for the SR-71 program, a specialized hydrocarbon so thermally stable that you could extinguish a lit match by dropping it into a container of the stuff. Fuel simply wouldn't ignite at normal temperatures. Its flash point exceeded 140 degrees Fahrenheit, compared to roughly 100 degrees for standard jet fuel. This thermal stability was absolutely essential, because the fuel did far more than just burn in the engines. It served as the aircraft's primary heat sink, circulating through hydraulic systems and electronics bays to absorb waste heat before reaching the combustion chambers. JP-7 flowed through channels in the aircraft's skin, carrying heat away from critical systems and distributing thermal loads across the airframe. By the time the fuel entered the engines, it had already absorbed so much thermal energy from various aircraft systems that it arrived preheated to several hundred degrees. This preheating actually improved combustion efficiency, turning what could have been a problem into an advantage. But JP-7's stability created its own challenge. How do you ignite a fuel that doesn't want to burn? The SR-71 used trethylborane TEB chemical compound that spontaneously combusts on contact with air. When TEB was injected into the engine, it would ignite instantly, creating temperatures high enough to ignite the JP-7. The aircraft carried enough TEB 416 engine start sufficient for normal operations plus reserves for in-flight relights if an engine flamed out. Pilots learned to husband this resource carefully. Use all 16 shots and you couldn't restart the engines regardless of how much JP-7 remained in the tanks. Running out of TEB at the wrong moment could turn a routine mission into a desperate emergency. The fuel capacity of the SR-71 was substantial, over 80,000 pounds in internal tanks distributed throughout the fuselage and wings. But fuel consumption at Mach 3 was prodigious. The aircraft would burn through its entire fuel load in roughly 90 minutes of cruise flight, necessitating multiple aerial refuelings for any significant mission. A typical reconnaissance sortie might require 3 or more refueling events. With KC-135Q tanker aircraft pre-positioned along the planned route, the refueling process itself was delicate and fuel-intensive. The SR-71 had to slow to subsonic speeds, connect with the tanker's boom, take on fuel, disconnect, and then accelerate back to cruise speed. Each refueling cycle consumed significant fuel just in the speed changes required. Every SR-71 mission was a continuous high-wire act across multiple engineering disciplines. Simultaneously metallurgy, thermodynamics, aerodynamics, chemistry etch, operating at absolute limits with minimal margin for error. And yet, for 30 years it worked. The engineering held. The aircraft performed. The question that would ultimately kill the program wasn't whether it worked, it was whether it was worth what it cost. When the SR-71 entered operational service in 1966, it gave American intelligence a capability that was literally untouchable. Nothing else in the sky could match it. Nothing on the ground could stop it. The aircraft would fly predetermined routes along the borders of denied territory, sometimes penetrating a few miles into hostile airspace, oozing
Looking cameras and sensors to photograph targets deep inside enemy territory without directly overflying them.
The reconnaissance systems could capture details from 80,000 feet with sufficient resolution to identify individual vehicles and read large markings. Soviet and Chinese air defense networks would detect the Blackbird immediately upon its approach. Despite some radar-absorbing materials on its surface, the SR-71 wasn't designed for stealth in the modern sense. Its radar cross-section was substantially far larger than today's stealth aircraft. It just didn't matter. Detection triggered a predictable cascade of responses. Threat radars would achieve lock. Missile batteries would prepare to fire. Interceptor aircraft would scramble desperately from airfields below. Warning lights and audio alerts would illuminate across the Blackbird's cockpit as the defensive systems cataloged each new threat, and then nothing effective would happen, or rather nothing that made any difference. The missiles would launch, climbing at maximum acceleration, rocket motors burning through propellant at prodigious rates as they clawed for altitude. A surface-to-air missile has to climb to altitude while simultaneously accelerating to intercept.
High-speed burning fuel continuously the entire time.
The SR-71 was already at altitude and already at cruise speed. By the time a missile fought its way up to 80,000 feet, it had exhausted most of its energy and was rapidly decelerating as its motor burned out. The Blackbird, meanwhile, was accelerating away at Mach 3+, opening the gap between aircraft and missile faster than any weapon could close it. The intercept geometry was mathematically impossible. Kelly Johnson had designed the aircraft specifically to exploit this fundamental reality of physics. Couldn't solve the problem by building a faster missile or a more powerful radar. The problem was in the mathematics of pursuit, and mathematics doesn't negotiate. Over Vietnam, the SR-71 demonstrated its capabilities in one of the most hostile air defense environments ever created by human beings. North. Vietnamese defenses were among the most concentrated and sophisticated in the world, a densely layered network of radar-guided anti-aircraft artillery. SA-2, surface-to-air missiles, MiG-17, and MiG-21 fighters, and thousands of smaller automatic weapons. This integrated system had already shot down hundreds of American aircraft during the conflict. The North Vietnamese had learned from years of combat experience, developing sophisticated tactics that coordinated multiple weapon systems into overlapping kill zones. MiG fighters would attempt to drive American strike aircraft down to altitudes where they became vulnerable to SA-2 missiles. Anti-aircraft artillery would force aircraft to fly higher into the engagement envelopes of the missiles. The layered defense was designed to create no-win situations for attacking aircraft. This system had driven American aircraft losses to unacceptable levels by the late 1960s. Tactical reconnaissance flights were being shot down with depressing regularity. Pilots were being killed or captured. Each mission, over heavily defended areas, was a dice roll against increasingly unfavorable odds. The SR-71 made all of this irrelevant. Major Brian Schul, who flew numerous missions over Southeast Asia, described a typical sortie over Hanoi. We'd enter North Vietnamese airspace at 80,000 feet in Mach 3. The entire country would light up every radar, every missile battery, everything they had. We'd photograph the whole country in about 15 to 20 minutes and leave before they could compute a firing solution that properly accounted for our speed and altitude. Their missiles would launch anyway, climbing toward us. We'd watch them come up and fall away, exhausted thousands of feet below us. It became almost routine. In one particularly well-documented mission over Haiphong Harbor in 1968, an SR-71 was targeted by 6 SA-2 missiles launched in rapid succession from multiple sites around the port. The pilot, monitoring his defensive systems, noted each launch but made no evasive maneuvers. There was no need. His response was simply to advance the throttles, slightly increasing speed from Mach 3.1 to approximately Mach 3.3, widening the already insurmountable gap between his aircraft and the pursuing missiles. He then continued his programmed reconnaissance route without any deviation from the mission plan. The missiles, pushed to their absolute maximum performance, exhausted their solid fuel propellant at altitudes between 60,000 and 70,000 feet still. 15,000 to 20,000 feet below the Blackbird and detonated harmlessly as their proximity fuses triggered in empty air, finding no target to destroy. The mission was completed exactly as planned. Complete photographic coverage of the target areas, zero damage to the aircraft, no genuine risk to the crew at any point. This pattern repeated throughout the Vietnam War until it became almost boring for the crews involved. In over 3,500 operational sorties during that era, the SR-71 never suffered combat damage, not a single bullet strike, not a missile fragment. Not even minor damage from the extreme conditions of Mach 3 flight through tropical thunderstorms. The safety record was perfect. Absolute. Unprecedented. Compare this to tactical reconnaissance aircraft like the RF-4C Phantom or RF-101 Voodoo, which suffered regular combat losses performing similar intelligence-gathering missions at lower altitudes. The contrast was stark and undeniable. Missions that cost conventional aircraft and their crews dearly. The SR-71 accomplished repeatedly, routinely, without any loss whatsoever. The intelligence gathered by these missions proved invaluable for American military operations. SR-71 imagery could reveal the movement of supplies down the Ho Chi Minh Trail, show the deployment of mobile anti-aircraft batteries before American strike packages arrived, identify new construction at airfields that might indicate arriving MiG reinforcements, and provide detailed bomb damage assessment after strikes. American commanders could task an SR-71 mission and receive processed imagery of North Vietnamese positions within hours, sometimes much faster if the mission was flown from a forward base with on-site film processing. This near real-time intelligence helped plan bombing campaigns, allowed strike aircraft to avoid newly deployed air defenses, revealed changes in supply routes, and provided commanders with an accurate picture of battlefield conditions. For military leaders desperate to reduce casualties while maintaining intelligence collection, the SR-71 seemed like the perfect solution in aircraft that could go anywhere, photograph anything, and return home safely every single time. But this tactical perfection masked strategic vulnerabilities that had nothing to do with enemy air defenses. The Soviet Union dedicated enormous resources to what they internally called the Blackbird problem. The strategic implications of their failure were severe and deeply embarrassing. If Soviet air defenses, the most extensive and sophisticated in the world, consuming massive portions of the defense budget, couldn't stop a single American aircraft, what did that say about Soviet military credibility? Every Blackbird overflight along Soviet borders was simultaneously an intelligence defeat and a propaganda humiliation. The response was systematic, determined, and extraordinarily expensive. The SA-5 Gammon system, designated S-200 in Soviet service, was deployed throughout the 1970s, specifically optimized for high-altitude, high-speed intercepts. The missiles were significantly larger than the earlier SA-2, with longer range, higher ceiling, and more sophisticated guidance systems. Soviet engineers had analyzed the SR-71's performance envelope and designed a system theoretically capable of reaching it. Theory and operational practice diverged sharply. The SA-5 could approach 100,000 feet in ceiling and achieve speeds that theoretically allowed Mach 3 intercepts. On paper, it should have been able to engage the Blackbird. But the missiles still faced the same fundamental physics problem that doomed every other system. The SA-5 had to climb to altitude while accelerating to intercept speed, burning propellant continuously throughout the engagement. By the time it clawed its way up to 80,000 feet, it had consumed most of its energy and was beginning to decelerate. The SR-71, already at altitude and cruise speed, could accelerate further if necessary, opening the gap faster than the missile could close it. The physics remained unchanged. Kelly Johnson's original insight still held: design an aircraft that operates beyond the performance envelope of the intercept geometry itself. The problem wasn't Soviet engineering. The problem was mathematics, and mathematics doesn't care how much money you spend. Soviet fire control radars would compute firing solutions. Missiles would launch with impressive fury. SR-71 crews would note the attempts in their mission reports and continue their assigned routes without deviation. The pattern became so predictable that experienced SR-71 pilots could often anticipate exactly when Soviet air defenses would fire based on their position relative to known SA-5 sites. The launches became almost a form of greeting, a predictable but futile gesture that posed no actual threat. The MiG-25 Foxbat represented the Soviet Union's attempt at an airborne solution to the Blackbird problem. Developed partially in response to American high-altitude reconnaissance aircraft and the proposed B-70 Valkyrie bomber, the MiG-25 was designed from the outset to reach extreme altitudes and speeds, could touch Mach 2.8 in short bursts, and briefly climb to 80,000 feet. Soviet propagandists announced triumphantly that the Foxbat would finally catch the elusive Blackbird. They were profoundly wrong. The MiG-25's impressive specification sheets concealed crippling operational limitations that made intercepts essentially impossible. The aircraft could only maintain maximum speed for a few minutes before its engines began to suffer serious damage from thermal stress. The Tumansky R-15 engines were powerful, but temperamental, optimized for high-altitude intercept profiles rather than sustained high-speed cruise. Push them too hard for too long, and turbine blades would crack, seals would fail, and engines would require complete overhaul or replacement. Fuel consumption at maximum speed was so extreme that effective combat radius was measured in tens of miles rather than hundreds. The MiG-25 would burn through its fuel load in minutes at full performance, leaving no margin for extended pursuit or multiple intercept attempts. Most critically, the MiG-25 couldn't sustain anything close to the SR-71's cruise performance. The Soviet interceptor might briefly accelerate to Mach 2.8, but the SR-71 cruised at Mach 3.24 hours. The MiG-25 might momentarily touch 80,000 feet in a zoom climb, but the SR-71 operated at that altitude for entire missions without strain. When Soviet interceptor pilots attempted to engage SR-71s, they would light full afterburner, climb as steeply as aerodynamics allowed, and burn through their fuel, trying desperately to reach a firing position. The SR-71 would simply maintain its cruise parameters already at altitude and speed and watch as the MiG fell away behind it. Engines overheating, fuel exhausted, defeated by physics before the engagement ever truly began. There are no confirmed cases of a MiG-25 ever achieving a successful intercept position against an operational SR-71. Not a single one, despite years of attempts. The closest Soviet interceptors came was detecting the aircraft on radar and launching missiles in pursuit, only to watch helplessly as the target accelerated away beyond reach. The radar operators and pilots could see the Blackbird. They simply couldn't touch it. The MiG-31 Foxhound, introduced in the 1980s as a substantially improved version of the MiG-25, featured a more powerful radar system and longer-range missiles specifically intended to engage high-altitude targets. But by the time it entered operational service, SR-71, operations were already being curtailed due to budget pressures and the growing availability of satellite reconnaissance. The MiG-31 never intercepted an SR-71 operationally, not because it was incapable, but because the opportunity never arose under conditions where an intercept was feasible. By the time the Soviets finally developed an aircraft that might have challenged the Blackbird was being retired. Some Soviet commanders became so frustrated with the Blackbird overflights that they ordered mass launches dozens of missiles at a single target, hoping that sheer volume might achieve what individual weapons could not. These salvos succeeded only in depleting Soviet missile inventories and providing American intelligence with invaluable data on launch procedures, radar frequencies, and system capabilities. In a notable incident over the Baltic in 1982, Soviet air defenses launched more than 40 missiles at a single SR-71 during one mission profile. Every single missile missed by substantial margins. The pilot later described the mission as sporty but never genuinely threatening. His defensive systems had provided ample warning of each launch, and the aircraft's speed advantage made evasion unnecessary. Meanwhile, those 40 missiles had provided American analysts with detailed information about Soviet launch coordination, missile performance characteristics, and radar tracking procedures. The SR-71 had photographed the missile sites in action, revealing their exact positions and operational patterns. The Soviets had spent tens of millions of dollars trying to kill an aircraft that was simultaneously gathering intelligence on exactly how they tried to kill it. The irony was complete. But here's where the story takes its crucial turn. Remember those 40 missiles over the Baltic? Each SA-5 cost the Soviet Union roughly $1 million in 1980s dollars. The entire salvo represented $40 million in expenditure and achieved absolutely nothing. No damage, no deterrence. Just 40 expensive missiles falling into the sea. The Soviets were losing the economic war against the SR-71. Every intercept attempt cost them dearly, while the Blackbird continued its mission undisturbed. What nobody realized at the time was that America was losing an economic war too. For all its invincibility in the air, for all its perfect safety record, for all its intelligence successes, the SR-71 had a weakness that would prove absolutely fatal to the program. This weakness wasn't technological. Couldn't be solved by better engineering, improved tactics, or upgraded systems. The weakness was economic, and it was killing the program more effectively than any Soviet missile ever could. The SR-71 cost approximately $200,000 to $300,000 per flight hour to operate. Let that number sink in for a moment. Every single hour the Blackbird flew, $250,000 evaporated into the sky. Not per mission, per hour. A typical reconnaissance sortie, lasting 3 to 4 hours, cost nearly $1 million in direct operating expenses alone before accounting for any support costs, infrastructure maintenance, or personnel training. To put this in proper perspective, the F-15 Eagle itself, considered one of the more expensive fighters to operate, cost roughly $30,000 per flight hour in that era. The SR-71 was almost 7 times more expensive per hour than an already expensive combat aircraft that could actually engage enemies. And these costs were constant, unavoidable, and essentially impossible to reduce through any efficiency measures. The specialized JP-7 fuel could only be produced at a handful of refineries equipped with specific distillation capabilities. The unusual chemical requirements meant limited production capacity and premium pricing. JP-27 cost several times more than standard military jet fuel, and the SR-71 burned through 80,000 pounds of it per mission. Each mission required multiple KC-135Q tanker aircraft positioned along the planned route for aerial refueling. These tankers were themselves specialized variants, extensively modified with equipment to handle JP-7 safely, different seals, different pumps, different procedures. They couldn't support conventional aircraft refueling and existed solely to keep the SR-71 operational. Each tanker required its own dedicated crew, its own maintenance, its own support costs. A single SR-71 mission might require 3 or 4 tankers, each representing additional millions in operating expenses. The titanium airframe required maintenance procedures utterly unlike any other aircraft in the military inventory. Every flight caused thermal cycles that stressed the metal in unique ways, creating fatigue patterns that had to be carefully monitored using specialized inspection techniques. The temperature extremes from ambient ground temperatures to 500 degrees at cruise caused expansion and contraction that gradually fatigued structural components. Inspection intervals were far shorter than conventional aircraft. Pairs demanded expertise that existed almost nowhere else in the world. Specialized welders, metallurgists, and technicians whose skills were applicable to no other program. You couldn't just transfer maintenance personnel from other aircraft. The SR-71 required years of specialized training. The Pratt & Whitney J58 engines required complete overhaul after relatively few flight hours, essentially being disassembled and rebuilt from scratch at enormous expense. Turbine blades, seals, and bearings degraded rapidly under the sustained thermal stress of Mach 3 operations. Only a handful of facilities in the entire country could perform these overhauls, each staffed with specialists whose knowledge was program-specific. The reconnaissance systems aboard the aircraft were constantly being updated and modified to keep pace with Soviet countermeasures and evolving intelligence requirements. Each upgrade required new development contracts, integration testing, and crew training. The specialized cameras used wet film technology that was becoming obsolete, requiring expensive modifications to remain relevant as digital imaging advanced. Perhaps most critically, the SR-71 required an entire support infrastructure that existed solely to keep it operational, an infrastructure that had to be maintained whether the aircraft flew frequently or rarely. Climate-controlled hangars protected the titanium airframes from thermal stress during ground operations. Specialized ground equipment worked with no other aircraft type. Supply chains maintained stocks of exotic components manufactured in tiny batches, sometimes individually fabricated because no commercial demand existed. Training pipelines took years to produce qualified pilots. The SR-71 required experienced aviators, typically with thousands of hours in high-performance aircraft, who then underwent extensive additional training specifically for the Blackbird. A year or more of preparation preceded operational missions. Each pilot represented an enormous investment that had to be maintained through regular flight hours, even when missions weren't required. Reconnaissance systems officers in the rear cockpit underwent similarly extensive preparation. Ground crews required specialized knowledge that took years to develop understanding of titanium metallurgy, familiarity with the J-58's quirks, expertise in handling JP-7 and TB safely. Beale Air Force Base in California housed the primary operational squadron, requiring extensive dedicated infrastructure. Kadena Air Base in Okinawa maintained a forward detachment for Asian operations, duplicating much of this infrastructure across the Pacific. RAF Mildenhall in England hosted aircraft for European missions. Each location required permanent staffing, specialized equipment, and continuous maintenance even during periods when missions weren't being flown. The fixed costs were enormous and essentially irreducible. You couldn't save money by flying less because the infrastructure costs remained constant regardless of operational tempo. This entire ecosystem existed for one aircraft type and could not be shared with any other program. Every dollar spent on SR-71 support was a dollar unavailable for anything else. When the Air Force conducted comprehensive cost analyses in the 1980s, the numbers were devastating. Total program costs, development, procurement, operations, and support infrastructure across 3 decades, it's $6 billion in inflation-adjusted dollars. Annual operating costs for maintaining the active fleet ran between $200 and $300 million, consuming a significant percentage of the entire reconnaissance budget. For this enormous expenditure, the Air Force was receiving approximately 30 operational reconnaissance sorties per year, sometimes fewer, depending on aircraft availability and mission requirements. 30 missions, $300 million annually. The mathematics was inescapable. Each SR-71 reconnaissance mission cost American taxpayers somewhere between $6 and $10 million. A single flight to photograph Soviet installations cost more than most Americans would earn in their entire working lives. This figure made even hardened Pentagon budget officers uncomfortable when laid out clearly. The aircraft that no Soviet missile could touch was vulnerable to something far more dangerous. Budget analysts armed with spreadsheets and pointed questions about cost-effectiveness. The question they asked was brutally simple. Could the same intelligence be gathered more cheaply by other means? The answer proved devastating for the SR-71 program. A reconnaissance satellite costs between $500 million and $1 billion to build and launch. At first glance, this figure seems comparable to SR-71 program costs, perhaps even more expensive. This superficial comparison misses the fundamental economic reality that would doom the Blackbird. A satellite operates continuously, 24 hours per day, 365 days per year, 4 years or even decades. It doesn't require tanker aircraft, doesn't burn specialized fuel, doesn't need maintenance crews or dedicated hangars or training pipelines. Once launched, a reconnaissance satellite's incremental cost per intelligence collection event is essentially zero. Just the expense of ground station operations and imagery analysis, which can be shared across multiple satellites. The satellite remains on station indefinitely, photographing its assigned targets every time its orbit brings it overhead, potentially multiple times daily, depending on orbital parameters and constellation design. Over a 15-year operational lifetime, a single reconnaissance satellite might conduct well over 100,000 intelligence collection events. The mathematics becomes overwhelming when you calculate cost per collection. An $800 million satellite conducting 100,000 imagery collections over its lifetime costs approximately $8,000 per event. The SR-71, at $6 to $10 million per mission, was roughly 1,000 times more expensive per intelligence product delivered. 1,000 times more expensive for each photograph, each piece of intelligence, each reconnaissance product. No amount of tactical brilliance, no degree of invincibility, could overcome arithmetic that lopsided. The SR-71 might outrun any missile, but it couldn't outrun that cost comparison. And satellite technology was advancing rapidly throughout the 1970s and 1980s, progressively eliminating every technical advantage the SR-71 could claim while maintaining that overwhelming economic advantage. Early reconnaissance satellites had been severely limited by technology. Systems like Corona and Gambit use film cameras that physically ejected capsules to deorbit and be recovered mid-air by specially equipped aircraft trailing grappling hooks. The process was cumbersome, time-consuming, and prone to failure. Capsules sometimes burned up on re-entry, splashed down beyond recovery range, or were damaged during the violent deceleration. By the early 1980s, this had completely changed. The KH-11 Kennan satellite, first launched in 1976, transmitted digital imagery to ground stations in near real time. No film capsules. No recovery aircraft. No delays waiting for processing. Commanders could receive satellite photographs within minutes of collection. Subsequent satellite generations improved resolution, added infrared and multispectral imaging capabilities, and dramatically increased data transmission bandwidth. By the late 1980s, satellite imagery resolution matched or exceeded what the SR-71's cameras could achieve from 80,000. VTAN continued improving with each new spacecraft generation. The operational advantages extended far beyond just cost. Satellites operate from space, entirely beyond the reach of terrestrial air defenses. No SA-5 missiles. No MiG-25 interceptors. No risk whatsoever from enemy action. A satellite constellation is inherently resilient. Losing one spacecraft to malfunction or natural causes doesn't eliminate the capability. The remaining satellites continue operating, and their orbits can be adjusted to compensate. Satellites could cover denied territory without any diplomatic complications. Unlike aircraft that technically violated airspace, satellites observed from orbital altitudes where no sovereignty claims applied. This eliminated the political risks that sometimes constrained SR-71 operations near sensitive borders. More importantly, satellites provided something the SR-71 could never deliver: persistent coverage. A Blackbird mission produced a snapshot record of conditions at one specific moment along one specific flight path. Valuable intelligence, certainly, but limited to that single point in time. Satellite photographs the same area every day, every orbit, building up a continuous record of activity. This persistence revealed patterns invisible to single-pass reconnaissance. Analysts could track the construction of military facilities over months, watching buildings rise and equipment arrive. They could observe seasonal changes in troop deployments, identifying training cycles and operational patterns. They could detect camouflage and concealment methods that might fool a single overflight, but became obvious when the same area was photographed repeatedly. Most critically, persistent surveillance could identify preparations for military operations. A single SR-71 photograph might show tanks in a depot. Daily satellite coverage would reveal those tanks moving to assembly areas, taking on fuel and ammunition, forming into combat formations, providing warning of impending action. This temporal dimension of intelligence transformed analytical capabilities in ways that mattered enormously to military planners. The SR-71 showed what was there at one moment. Satellites showed what was happening over time. Modern reconnaissance satellites carry multiple sensor types beyond visible light cameras. Synthetic aperture radar images the Earth's surface, regardless of weather or darkness, providing all-weather day and night coverage that optical systems cannot match. Infrared sensors detect heat signatures from vehicles, aircraft, and industrial facilities. Signals intelligence satellites collect communications and electronic emissions across entire continents simultaneously. The SR-71's sensor suite, while sophisticated for its era, was fundamentally limited to what could fit aboard a single aircraft flying a single mission profile. Satellites could be specialized for different collection tasks and operated as coordinated constellations, each spacecraft contributing specific capabilities to a comprehensive intelligence picture. The SR-71 had been designed for an era when satellites were primitive, unreliable, and limited in capability. In the early 1960s, manned reconnaissance aircraft were the only way to collect detailed intelligence over denied territory. The Blackbird was the ultimate expression of that approach, faster, higher, and more capable than anything else in the sky. By the 1980s, the strategic environment had fundamentally transformed. Satellites could cover more territory more frequently with no risk and dramatically lower cost. They couldn't be shot down by air defenses. They didn't require tanker support. They could observe areas of interest continuously, providing persistent surveillance that no aircraft could match regardless of speed or altitude. The SR-71's unique advantage, its ability to operate with impunity in the most hostile environments, was becoming strategically less relevant as satellite capabilities improved. The handful of scenarios where manned reconnaissance offered genuine advantages over space-based collection were increasingly difficult to justify at $200,000 per flight hour. Defense budget pressures in the late 1980s made these cost equations impossible to ignore. The Cold War was winding down. Congress demanded peace dividends. Every program faced intense scrutiny, and programs with high costs and declining strategic relevance became obvious targets. The SR-71 found itself in precisely that category. In 1989, the Air Force announced the retirement of the SR-71 fleet, citing budget constraints and the availability of satellite reconnaissance as viable alternatives. The aircraft would be placed in storage. The specialized infrastructure would be dismantled. The era of manned strategic reconnaissance appeared to be ending. The announcement sparked fierce debate within the intelligence and defense communities. Program defenders argued passionately that the SR-71 provided unique capabilities no satellite could: replicate tactical flexibility, rapid response to emerging situations, the ability to collect intelligence on short notice without waiting for orbital mechanics to bring a satellite overhead. These arguments had genuine merit. Satellites follow predictable orbits that adversaries can track and plan around. The SR-71 could appear over a target with minimal warning. Satellites are vulnerable to weather and cloud cover. The SR-71 could fly below obscuring cloud layers in certain situations. Some intelligence targets were better served by manned reconnaissance than orbital platforms, but none of these arguments could overcome the fundamental economic reality. The program cost too much for what it delivered. Alternative collection methods could accomplish most missions at a fraction of the expense, Every dollar spent on the Blackbird was a dollar unavailable for other intelligence capabilities that provided better returns. The opportunity cost was simply too high to justify. The story doesn't quite end with the 1989 retirement. In 1995, political pressure led to the senior S-71's brief reactivation. Congress, responding to advocacy from some intelligence community officials and aerospace industry interests, mandated returning 3 aircraft to operational status. The legislation specifically required the Air Force to reconstitute at least a limited SR-71 capability. The Air Force complied, though with notable reluctance. The reactivated aircraft flew a handful of missions over the following years. But the economic fundamentals hadn't improved. If anything, they had deteriorated significantly. The support infrastructure had been partially dismantled after the 1989 retirement. Qualified pilots and maintenance personnel had scattered to other assignments or retired from service. Specialized supply chains had contracted or disappeared. Reconstituting even partial operational capability required enormous effort and expense rebuilding what had been deliberately disassembled, retraining personnel who had moved on, reestablishing supply relationships that had lapsed. By 1998, the Air Force had accumulated sufficient operational data to make its case definitively. The reactivated SR-71s were flying approximately 10 missions per year at best. Total annual program costs exceeded $300 million. Simple division yielded a figure that ended all debate, roughly $30 million per mission. $30 million for a single reconnaissance sortie. Even the senior 71's strongest advocates struggled to construct an argument justifying that expense when alternatives existed. Congress relented. The SR-71 was permanently retired in 1998, with no possibility of future reactivation. The last operational flight occurred on October 9, 1999, a NASA research mission from Edwards Air Force Base. The aircraft was then formally retired and placed on permanent display, ending one of the most remarkable chapters in aviation history. Here's the profound irony at the heart of this entire story. The U-2 slower lower. More vulnerable aircraft, the SR-71 was specifically designed to replace still flies operational reconnaissance missions today, more than 60 years after entering service. The U-2 costs approximately $40,000 per flight hour to operate, 1/5 of the senior 71's expense. For the price of a single Blackbird mission, the Air Force can fly 5 U-2 sorties, each providing significantly longer loader time over the target area and comparable imagery resolution. The U-2 can't outrun missiles, can't cruise at 80,000 feet for hours, remains fundamentally vulnerable to modern air defenses, in ways the SR-71 never was. If the Soviets had dedicated equivalent resources to killing U-2 south in the 1980s, they might well have succeeded. But the U-2 is economically sustainable. It can be operated routinely, regularly, without consuming vast portions of the reconnaissance budget. Its lower performance comes with proportionally lower costs that allow consistent operational use. And so the aircraft, designed to be utterly untouchable, sits silent in museums across America. The aircraft it was meant to replace keeps flying combat missions. The lesson couldn't be clearer or more uncomfortable. When I examine the complete arc of the SR-71's story, what emerges is a narrative far more complex and instructive than simple tales of invincibility. The aircraft achieved something genuinely extraordinary. For 3 decades, it operated in the most hostile airspace on Earth without a single loss to enemy action. It outran thousands of missiles. It frustrated entire air defense networks built specifically to destroy it. It collected intelligence that helped America navigate the most dangerous decades of human history. These achievements were real and permanent. The engineering was magnificent beyond anything attempted before or since. The operational record was perfect and unprecedented. But the program's termination reveals an equally important truth about military power that often gets overlooked in favor of more dramatic narratives. Technological superiority alone doesn't ensure survival. Economic sustainability matters profoundly. Strategic relevance matters. Opportunity cost matters. The context in which a system operates matters as much as the system's raw capabilities. The SR-71 could outrun any missile ever built, but it couldn't outrun the spreadsheet. Its titanium skin could withstand 900-degree temperatures, but it couldn't withstand cost-benefit analysis. Its speed made it invincible against Soviet air defenses, but speed offered no protection. Against budget analysts asking uncomfortable questions about value delivered per dollar spent, 4,000 missiles couldn't kill the Blackbird. 40 years of Soviet engineering effort couldn't produce a system that threatened it. But accountants with calculators brought it down in less than a decade once they started examining the numbers seriously. This pattern has repeated throughout military aviation history and continues shaping procurement decisions today. The B-2 Spirit stealth bomber costs approximately $130,000 per flight hour to operate. The original program called for 132 aircraft. Budget realities slashed that to just 21. Each B-2 is so expensive to operate and so irreplaceable that commanders hesitate to risk them on any but the most critical missions. The world's most advanced bomber spends most of its operational life sitting in climate-controlled hangars. The F-22 Raptor is arguably the most capable air superiority fighter ever built, a genuine generational leap in aerial combat capability. But at $70,000 per flight hour, the fleet was capped at 187 aircraft rather than the 750 originally planned. Cheaper alternatives like the F-35, despite lower performance in certain metrics, are being produced in far greater numbers because they can actually be sustained operationally. An invincible weapon you can't afford to use regularly is operationally equivalent to having no weapon at all. Capability that exists only on paper or only for the most critical contingencies provides limited deterrent value and no day-to-day utility. The same tension shapes current debates over sixth-generation fighters, hypersonic weapons, and advanced autonomous systems. Each promises decisive advantages. Each carries cost projections that may ultimately prove unsustainable. The Senior 71's ghost haunts every Pentagon procurement meeting, whispering the same warning that went unheeded for too long. Capability without sustainability is capability you'll eventually lose. The future of reconnaissance and, increasingly, of military operations generally, appears to be moving decisively away from the SR-71 model of concentrated excellence. Rather than focusing extraordinary capability in a few irreplaceable platforms, modern systems increasingly distribute capability across many cheaper assets. Constellations of dozens or hundreds of satellites, rather than a few exquisite spacecraft. Swarms of expendable drones rather than irreplaceable manned aircraft. Networks of sensors feeding common processing systems rather than isolated collection platforms. This distributed approach offers economic advantages that the SR-71 model never could. Losing one asset doesn't cripple the entire capability. Redundancy is built into the architecture. Costs scale more linearly with capability. Individual platforms can be risked more freely because they're replaceable. The Global Hawk reconnaissance drone costs roughly $20,000 per flight hour and can remain on station for over 30 hours continuously. A fleet of Global Hawks can maintain persistent coverage that no manned aircraft could match at a fraction of the cost of a single SR-71 mission. The Blackbird model, magnificent capability concentrated in an unsustainably expensive platform, increasingly appears as a historical artifact of a specific technological and strategic moment that has passed. Brilliant engineering that ultimately proved strategically unviable in a changed world. Yet something was genuinely lost when the Blackbird retired. Something that resists easy quantification in cost per flight hour metrics. Colonel Buzz Carpenter, who flew 127 operational missions in the SR-71 over his career, once described the experience of piloting the aircraft. At 85,000 feet, you could see the curvature of the Earth clearly. Sky above wasn't blue anymore, it was black, and you were looking into space. Below, weather systems that terrified pilots in normal aircraft looked like abstract paintings, impossibly distant and irrelevant. And you were moving faster than anything else in that sky, faster than the missiles climbing toward you, faster than the physics that governed ordinary aircraft. For a few hours, you existed in a realm that belonged only to you and perhaps a dozen other human beings in the world. Nothing else flew where you flew. Nothing else could. The men who flew the Blackbird speak of it with a reverence that approaches the spiritual. They had touched something at the absolute edge of human engineering achievement. They had operated machines that pushed every physical law to its limit and beyond. They had traveled to regions of the sky that remain forever closed to almost everyone else who has ever lived. That experience is gone now, replaced by operators in air-conditioned rooms controlling satellites with keyboards and monitoring drone feeds on screens. The intelligence collection continues better and cheaper and more comprehensive than the SR-71 ever achieved. But something irreplaceable departed when the last Blackbird landed. The pilots who once outran missiles at the edge of space now walk through museums, looking up at the silent aircraft that gave them transcendence, grounded forever by the one enemy their magnificent machines couldn't outrun. The SR-71 Blackbird was invincible in the air, legendary in its performance, unmatched in its capabilities. 4,000 missiles couldn't touch it. The combined air defense networks of the Soviet Union, China, North Korea, and North Vietnam couldn't threaten it meaningfully. For 30 years, it operated with a perfect safety record in the most hostile airspace on Earth, collecting intelligence that helped prevent nuclear war and shape the course of history. And yet it's dead, grounded, a museum piece while lesser aircraft continue flying. The fatal weakness wasn't technological. Soviet engineers never solved the Blackbird problem despite decades of effort and billions in expenditure. Their missiles never came close. Their interceptors never achieved firing position. Their radar systems could track it, but not catch it. The fatal weakness was economic. The SR-71 cost too much for what it delivered compared to alternatives. Satellites and drones could accomplish similar missions at a fraction of the expense. Every dollar spent on the Blackbird was a dollar unavailable for capabilities that provided better returns on investment. The aircraft that couldn't be shot down was ultimately grounded by the one weapon it had no defense against: the budget. That's the real story of the SR-71, not just a tale of technological triumph, but a profound lesson in the limits of invincibility and the inexorable power of economic reality. The titanium giant sits silent now in museums across America. The Smithsonian, at Wright-Patterson, at Duxford in England, at dozens of other locations where they've become monuments to an extraordinary era. Visitors walk around these magnificent machines, marveling at their sleek forms, imagining them screaming across the stratosphere at 3 times the speed of sound, outrunning missiles and defying physics, and mocking the most sophisticated air defenses ever built. They should also remember what brought these magnificent machines down. Not Soviet engineering, not advanced missiles, not breakthrough radar systems, it's not the combined military might of the Eastern Bloc. Something far more prosaic destroyed the SR-71, the cold logic of cost per mission, and the emergence of alternatives that could accomplish the job more cheaply. That's the fatal weakness that no amount of titanium armor or Mach 3 speed could overcome. 4,000 missiles couldn't kill the SR-71. The spreadsheet could.